Okay, our first talk is from Tom Rudelius, who's going to tell us about eternal inflation and Antisitter Bounds from dimensional reduction. Take it away, Tom.
Okay, thanks a lot, Cody, and thank you for the invitation. My talk today is going to be based primarily on this pair of papers that I wrote in 2019 and 2021. A quick outline for where we're headed today. I'm going to start out by introducing some de Sitter and anti-de Sitter swampland conjectures. I'm going to relate these to dimensional reduction. I'm going to talk about conditions for eternal inflation, and then I'm going to tie all of this together with some speculations. So first of all, let's talk about some anti-de Sitter swampland bounds. Over the last few years, there have been a few de Sitter conjectures coming primarily from Vafa and collaborators, which have gathered a lot of attention in the community. So the first one, called the de Sitter conjecture, is a lower bound on the gradient of the scalar field potential in quantum gravity in terms of the potential itself. So morally, what this bound is saying is that you can't have too shallow of a slope of your scalar field potential. It needs to be sufficiently steep. The refined de Sitter conjecture came a little bit later. These people said that either this condition should hold or this condition should hold. There should be an upper bound on the smallest eigenvalue of the Hessian of the scalar field potential. So this bound here would allow for critical points, but it would rule out minima. It would even rule out maxima of the potential, or saddle points, that if they're not tachyonic enough. They say that you really need a really steep hilltop like this. I should mention there's another version of the de Sitter conjecture, the refined de Sitter conjecture from David Andriott, where he took these conditions and put them into a linear combination, but the effects are roughly the same as condition 2. There's another anti-de Sitter distance conjecture that was proposed by these authors in 2019. And what this conjecture says is that when you have some ADS, or perhaps some DS vacuum with cosmological constant lambda, there should be a tower of states in the theory who with a mass scale which is set by the cosmological constant to some power alpha. And this alpha, like the parameters C and C prime here, are order 1 constants to be determined later. Now, a few remarks about these conjectures. First of all, if they're true, they would have enormous implications for how we understand our universe, for how we understand cosmology and inflation and dark energy. And this is why these conjectures have gotten so much attention in the last few years, especially from the cosmology community. On the other hand, there's this sort of famous swampland trade-off. The conjectures that tend to have more evidence in their favor tend to be less interesting. Conjectures like these that tend to be more interesting tend to have less evidence in their favor. They're true under the lamppost, but there's a high likelihood of a lamppost effect going on here, so that the statements that we've just seen may have only some limited domain of validity within quantum gravity. In order to understand what this domain of validity is, the first thing we need to do is understand the underlying physical motivation behind these conjectures. And this is really, I think, what is lacking at present from these statements. And to clarify this, I want to contrast the case of the de Sitter conjecture with the weak gravity conjecture, which is another swampland statement, which I would say is on much more rigorous footing. Much more evidence, as well as in bottom-up type arguments, have been given in support of the weak gravity conjecture. And the weak gravity conjecture is a statement that has a clear physical motivation. The idea that originally motivated it was the statement that black holes should be able to decay. Now, it isn't entirely clear why quantum gravity should insist that black holes decay, but nonetheless, this is a sharp condition. This is something that the quantum gravity might have an issue with, and it seems to have got us to start digging in the right place. Relatedly, this sharp physical condition gives rise to a sharp inequality on the charge to mass ratio of a particle. The weak gravity conjecture says that you need a particle which satisfies this bound, Q over m is greater than or equal to some order 1 number in Planck units. And this isn't some order 1 number to be fixed later. This is a number that we know how to compute in 4 dimensions, for instance, without any massless scalar fields. It's the square root of 2. Now, this is to be contrasted with the case of the de Sitter conjectures. Here, we don't have some sharp order 1 coefficients. we have these order 1 coefficients to be determined later. And relatedly, we don't have some sort of clear physical motivation. There isn't some physical property which is satisfied if these bounds are exactly saturated or satisfied, and violated if these bounds are marginally violated. So that's what we'd really like to make progress here, to perhaps put these conjectures on more solid footing, is to figure out what is the underlying physical mechanism that ideally fixes some of these order 1 coefficients. So with that, I want to introduce the idea of dimensional reduction for fixing swampland coefficients. And it's best to consider how this works in the case of the weak gravity conjecture, where it's been understood for a number of years. Suppose we start with this theory in d dimensions. So we have the Einstein-Hilbert term, we have a massless scalar field, the dilaton, and this massless scalar field couples to this Maxwell term here via this exponential coupling. This is the Maxwell term for a p-form gauge field. There are charged p-1 branes, and the weak gravity bound is a bound on the charge to tension ratio in terms of this order 1 coefficient gamma, which again can be computed in terms of the dimensionality of the brane, the dimensionality of space-time, and this coefficient alpha. And this bound and this coefficient have the remarkable property that if you compactify this theory on a circle, the resulting gamma that you get is exactly the same as the gamma that you started with. And that happens whether you decrease p by taking one direction of the brane to wrap around the compactified circle, or if you take all of the directions to lie in non-compact directions. And in either case, gamma is exactly preserved, which means that the weak gravity conjecture is exactly preserved under dimensional reduction. In other words, the parent theory will satisfy the weak gravity conjecture if and only if the resulting theory after dimensional reduction satisfies it. So another way to understand this, what it's telling us, is that the weak gravity conjecture, the dimensional reduction is picking out the correct statement of the weak gravity conjecture. Even if you didn't know this gamma ahead of time, if I didn't show you this formula, but I told you that the weak gravity conjecture should be exactly preserved under dimensional reduction, you'd actually be led to this value here. So the hope is maybe we can do a similar thing with these other conjectures. So let's start with the de Sitter conjectures. We start with an action of this form. It has gravity. It has a collection of scalar fields with a scalar field potential. And we're going to assume a bound of this form, like the one that shows up in the de Sitter conjectures, lower bound on the gradient of the potential. Here, we're going to have the potential raised to some power gamma, where gamma is some order 1 number to be fixed later, and CD here is this order 1 coefficient also to be fixed. So we compactify this on a circle, and what you find is that the R dependence, the dependence on the radius of the circle, exactly cancels when gamma is equal to 1. So in other words, dimensional reduction is picking out this particular value of gamma. And notably, this is the value that shows up in the de Sitter conjecture. The de Sitter conjecture is a lower bound on the gradient of the potential in terms of the potential to the first power. Now, when you perform this reduction, you get a new scalar field, which is the radion, and that's going to contribute to the potential. And what you find, including the radion, is that the coefficient C, which is exactly preserved, is given by this expression here. So if C is given this expression in d dimensions, then this bound will be exactly preserved under dimensional reduction. Here, beta is some number. That can be anything you want, but beta equals 0 is special in that it's the smallest value of beta, such that CD squared is non-negative as d goes to infinity. And if you plug in beta equals 0, what you find here is that this condition is exactly the condition that forbids accelerated expansion of the universe. So, like with the weak gravity conjecture, where dimensional reduction picks out the black hole extremality bound, here, dimensional reduction is once again picking out a physically relevant value, namely the value that shows up in the de Sitter conjecture for gamma and the value of C that forbids accelerated expansion. A similar analysis can be applied for the anti-de Sitter conjectures, starting with an action with a cosmological constant, a tower of massive fields, mass scale set by the cosmological constant, alpha to be fixed later, we find that this bound here is exactly preserved when alpha is equal to 1/2. And this is another interesting value. This is what the authors called the strong ADS distance conjecture value. And it's satisfied in all supersymmetric ADS vacua for which we have well understood uplifts to 10 and 11 dimensional supergravity. So for instance, this is violated in KKLT, which does not at present have a well understood uplift. Now, this previous slide here was done entirely at the classical level, but at the classical level, the radion is not stabilized. And so if we actually want an ADS or a DS vacuum in lower dimensions, we need to stabilize the radion. And the easiest way to do this is to include the effects of the Casimir energy at one loop, which looks like this. It gives a competing contribution to the potential for the radion lambda. And when the dust settles, what you find is that there's another value which is distinguished by dimensional reduction, which is alpha equals 1/d. This is another physically interesting value because of the possible connection to neutrino physics. In our universe, the mass scale of neutrinos is roughly on the order of the cosmological constant to the 4th power. Okay, so that's what I wanted to say about dimensional reduction. Now let me switch gears a bit and talk about conditions for eternal inflation. So to remind you, inflation describes this period of quasi-exponential growth of the universe. The scale factor is growing almost exponentially. H here, the Hubble parameter, is almost a constant. In field theory, it can be thought of as simply the theory of a ball that's rolling down a hill with friction. The equation of motion is exactly the equation of motion for a ball with friction. And here, the friction term, H, is set by the sum of the kinetic energy and the potential energy of this ball. Inflation occurs when the ball is rolling slowly. In other words, when the slow roll approximation is valid. So this occurs when the kinetic energy of the ball is dominated by its potential energy. And this term in the equation of motion is smaller than these two. So if we make these approximations and plug them in to the equations of motion, we find that the equation of motion for the scalar field is simply a gradient descent. This is the equation for a gradient descent, where h here is given by h squared equal to 1/3 v. So in order to go from the classical analysis of inflation to eternal inflation, we need to include quantum back reaction. So what happens during inflation is that there are these tiny little quantum fluctuations, and during inflation, these tiny quantum fluctuations are stretched out. They become larger than the horizon. They deco here. And the idea behind stochastic inflation is to approximate the back reaction of these quantum modes, which have decohered as a classical noise term in the equation of motion. So what this means is that the dynamics of this scalar field are going to be governed by two effects. First of all, you have the classical rolling. The field rolls down the hill via a gradient descent. But also there are these quantum fluctuations, which are Gaussian distributed. They have mean 0, so they have equal probability of pushing you down the hill or up the hill, and they have a variance given by this expression here. Now, the equation that describes the probability density function of such a situation is called the Fokker-Planck equation. The Fokker-Planck equation is a little bit complicated. It looks like this, but you can see here that there are these two terms in it. The first one comes from the quantum fluctuations, and classical evolution. In general, this equation is difficult to solve numerically, but if we make the assumption, which is valid during inflation, that h is a constant, then there are two cases where this equation can be solved analytically: the case of a linear potential or the case of a quadratic potential. And fortunately for us, these are precisely the cases of most interest. In both cases, the solution to the Fokker-Planck equation is simply a Gaussian. So it's this Gaussian PDF right here. There's a mean mu, there's a standard deviation sigma. These things evolve in time, and their evolution, of course, is different for the linear potential and the tachyonic potential. It's easiest to understand these in pictures. So in the case of a linear potential, if the field starts up here at time 0, then as time goes on, classical evolution means that the field will roll to the right. The mean will increase. At the same time, though, the quantum fluctuations mean that this probability density function will spread out as the variance increases linearly in time. So as time goes on, you're going to move down here, but the wave packet will get flatter and flatter. For the tachyonic potential, if you start the field at t at the top here at t equals 0, then the mean will remain 0 for all time by symmetry, but the variance will grow as the wave packet flattens out. And in fact, it will grow exponentially in time. The way to understand this is that starting from the top, at some point, a quantum fluctuation will push you a little bit to the left or a little bit to the right. And very shortly thereafter, classical evolution takes over and very quickly pushes you far to the right or to the left. So inflation, as I said, occurs when we're in the slow roll regime, which means that the field is rolling slowly. Its first derivative, the first derivative of the potential, is small relative to the potential itself. In the case of the linear potential, this occurs when you're sufficiently high up on the potential, in this blue region here. In the case of the tachyonic potential, inflation occurs when you're sufficiently close to the top of the hill. So if we want to know what is the probability that inflation is occurring at time t, we should integrate over phi from negative infinity to this value phi end. If the field is located somewhere in here, inflation is occurring. And we can actually just do this computation because remember, we have this analytic Gaussian solution for P. And so we can integrate this Gaussian distribution. That's going to give us an error function, or C. And as t gets large, we can approximate this as this exponential decay. So as t goes to infinity, the probability that inflation occurring goes to 0. And this makes sense physically. As time goes on, the mean of this Gaussian is going to be further and further to the right. And so the probability that you're lying here in this tail is going to get smaller and smaller. And indeed, it's going to decay exponentially in time. So you might look at this and say, well, it looks like inflation is going to end after finite time with probability 1. What do you mean by saying that we have eternal inflation? But the point here is that you need to remember that although the probability of inflation for a particular observer may be going to 0 as t goes to infinity, we also have this competing effect, which is the exponential growth of the universe. So inflation is ending in most points in space due to this exponential decay, but new space is being created at this exponential rate. And so the question of whether or not inflation is eternal amounts to the question of which of these effects wins. Is it the exponential growth of the universe, or is it the exponential decay? So if 3h is larger than this expression here, inflation lasts eternally. And the cartoon picture, I think, is worth having in your head. What happens in a given e-folding, perhaps inflation ends in most regions, but due to the quantum fluctuations, in some regions, the scalar field gets pushed further up the potential. And these regions will continue to inflate, and the same story takes place. In most regions, inflation will stop, but in some, it will keep going. And you can probably already see that we're developing this fractal-like structure. We end up with this, this fractal-like structure at late times, which gives rise to this eternal inflation multiverse. So that's the cartoon picture. Now, we just worked out this condition for eternal inflation. And if we now take this and plug in a bubble parameter in terms of the potential V, and we plug in for alpha in terms of the derivative of the potential, this condition becomes a lower bound on the first derivative of the potential in terms of the potential itself. This bound was previously derived by these authors using more sophisticated methods, but we see here that the relevant physics can actually just be captured by this simple computation. We get the exact same result. A similar analysis can be carried out for the tachyonic potential. Inflation will be eternal if this bound is satisfied. And plugging in, we find that inflation lasts eternally if we have this lower bound on the second derivative of the potential. So in other words, the potential can be tachyonic, V double prime can be negative, but it can't be too negative. In my more recent paper from this year, I extended this analysis from 4 dimensions to D space-time dimensions. It's a simple generalization. We get the same sorts of formulae. You'll note that the coefficient has changed from 3/2 to D plus 2 over 2. And of course, this order 1 coefficient is a little bit more complicated, but same sorts of physics. Okay, so all of the computations that I've done so far have been very sharp and precise computations. We worked out the conditions for eternal inflation in 4 and more generally in arbitrary D space-time dimensions. We performed these dimensional reductions. We considered how some bounds changed. Now I want to get into some speculations about what this might mean for the Swampland program. So first of all, you remember what motivated this whole talk was the question of trying to find some sort of underlying physical motivation for the de Sitter conjectures. And from what we've seen, I want to posit that there are 3 noteworthy possible physical motivations that are worth discussing. The first one, which I mentioned in this paper from 2019, is the no eternal inflation condition. So this is a principle, the idea that inflation cannot be eternal, which has been discussed in past literature for decades. But what we see here, what's noteworthy, is that the bounds that we get for no eternal inflation, which we obtain just by taking the eternal inflation bounds and changing the signs, making the greater than sign less than and vice versa, we find bounds that look very similar to the de Sitter conjecture bounds. So the de Sitter, in particular, the refined de Sitter conjecture is either a lower bound on the gradient of the potential in terms of the potential, or it's an upper bound on the second derivative of the potential divided by the potential. And so we're getting very similar sorts of bounds here. No eternal inflation says that either this must be satisfied or this must be satisfied. So perhaps no eternal inflation is the right refinement of the de Sitter conjectures. It's nice in that it gives us these precise order 1 coefficients. It's a nice physically well-motivated principle. And even though there isn't any obvious reason why quantum gravity would have an issue with eternal inflation, it's at least the sort of thing that quantum gravity might try to avoid, because eternal inflation leads to a very different asymptotic structure of space-time at late times than the space-times that we're accustomed to seeing in quantum gravity. Now, on the other hand, from the perspective of dimensional reduction, it's worth noting here that we have this power of 3/2. So this is different. This is really the key difference between this and the de Sitter conjectures. The de Sitter conjectures have a v to the first power, whereas this has a v to the 3/2. So this bound is actually much easier to satisfy than the de Sitter conjectures. And in general, the refined de Sitter conjecture is strictly stronger than this statement. So it implies no eternal inflation. But we saw that the de Sitter conjecture itself is the thing that actually behaves nicely under dimensional reduction. The fact that we have this 3/2 here instead of the first power, and more generally we have d plus 2 over 2 in 2 dimensions, means that this condition is going to be consistent under dimensional reduction, but it's not going to be exactly preserved. So if I start with a theory in d plus 1 dimensions that satisfies no eternal inflation, and I compactify, I still won't have eternal inflation, but I won't satisfy the condition marginally. Now, perhaps going in the right direction and thinking more about this result, Alec Bedroya and Kamran Bafa, the translating cosmic censorship conjecture. And the one advantage of this, I would say, perhaps the one big advantage relative to this one, is that we're getting the first power here that we had in the de Sitter conjectures, and which is exactly preserved under dimensional reduction. On the other hand, this coefficient here is not exactly preserved under dimensional reduction. Like this bound will be consistent under dimensional reduction. If we satisfy Transplanckian cosmic censorship conjecture in d plus 1 dimensions, we'll still satisfy it after dimensional reduction, but not marginally so. The statement which is exactly preserved is this other physical condition, the statement of no accelerated expansion. So if your theory saturates this bound in d+1 dimensions, it will still saturate it in d dimensions. Now, the problem with this one, although it's nice and physically motivated, it's obviously not true in our own universe. We live in a world that is experiencing accelerated expansion. So this statement, although it's preserved under dimensional reduction, cannot be true in general. Nonetheless, it is possible that such a statement might be true, for instance, in asymptotic regions of scalar field space. This is something worth stressing once again. The de Sitter conjectures may have a limited range of validity. They might not be true generically in quantum gravity. They may be true, for instance, only in asymptotic regions of scalar field space. So I think it would be interesting at least to pursue this further and to see if perhaps there's some reason why quantum gravity would not allow accelerated expansion in such asymptotic regions of scalar field space. Okay, I'll go more quickly. So for the ADS distance conjecture, similarly, dimensional reduction picked out two interesting values of this coefficient. The first one is the strong ADS value of 1/2. This is possibly related to supersymmetry, but this cannot be satisfied in our own universe. Another more phenomenologically interesting value, which is picked out by dimensional reduction, is lambda to the 1/d. The physical motivation for this is rather unclear, but it's nice in that it may relate the neutrino masses to the cosmological constant. And via the seesaw mechanism, this would further relate the Higgs vev to the cosmological constant and therefore correlate the hierarchy problem and the cosmological constant problem. This, I would say, is a very speculative relationship, but it's maybe worth pondering further. So let me conclude. We considered and we worked out the conditions for eternal inflation. We found that it imposes constraints on the first and second derivatives of the scalar field potential, which is very reminiscent of the refined de Sitter conjectures. We found that dimensional reduction distinguishes the correct order 1 coefficients of the weak gravity bound. And this led us to consider such a dimensional reduction analysis for these de Sitter conjectures. We found that it distinguishes certain physically relevant values of the coefficients in these conjectures, but whether or not these values are correct, what exactly the correct version of the de Sitter or ADS distance conjecture is, what the correct physical motivation is, what the domain of validity is, these are the important questions that remain to be seen. Thank you.
All right, thank you, Tom, for the very nice talk. Let us all thank Tom with our clap emojis. Our first question comes from David.
Hi. Thank you very much, Tom, for the nice talk and nice results. I was not sure to understand your point about beta being equal to 0 because of forbidding the accelerated expansion. So I would think that any positive coefficient in the right of the inequality would forbid accelerated expansions. I'm not sure why you should fix beta equals to 0.
Okay, yeah, thanks. Good. So you're right. Any positive beta here would forbid accelerated expansion. For beta negative, of course, that would not be the case. So I want to fix. So in order to relate this to accelerated expansion, beta would have to be greater than or equal to 0. But I think what's especially interesting is that beta equals 0 is exactly the condition. It's the statement that precisely forbids accelerated expansion of the universe. So remember, the goal here, as in the case of the weak gravity conjecture, is to see if there's some physical principle which would lead to these bounds. Some more physical reason why they should be true, something which is marginally true if the conjecture is marginally satisfied, and it's marginally false if the conjecture is marginally violated. And so what I think is nice here is that beta equals 0 is the smallest value such that this remains non-negative for all d. And it also coincides with this physical principle of no accelerated expansion. So to me, that's a connection that's at least worth noting and pointing out. And it suggests that if any of these values of beta is the right value, it's probably beta equals 0.
Thank you.
Okay, if there are no further questions for Tom, let us thank Tom again for the very nice talk.